Next chapter, trigonometric ratios. So far, we know how to find the trigonometric ratios of angles between 0 and 90 degrees. So if you have a triangle and you have an angle, and because it's right triangle, theta will be between 0 and 90 degrees. This is opposite, adjacent, and hypotenuse. Sin theta is equal to opposite over hypotenuse, because theta is equal to adjacent over hypotenuse, and tan theta is equal to opposite over adjacent. But perhaps you might have come across a question requiring the student to find the sine or cosine of an angle greater than 90 degrees, or even a negative angle, and you might have wondered, what's that? Well, it's possible. In this chapter, we are going to expand the definitions of trigonometric ratios to apply to every angle. We use a unit circle, and this is how we do it. Basically, we start with the Cartesian plane or the XY plane. We take one unit from the center to all axes, and then using this radius, we draw a circle. This is a unit circle, a circle with a radius of 1 unit. Unit means 1. So the XY axis divides the unit circle into 4 quarters called quadrants. The first quadrant is called A, second quadrant is S, third quadrant is T, and fourth quadrant is C. Some books may label them A, B, C, D, but ASTC is convenient for some reason I will tell you later. Angles in this unit circle are measured from the positive side of the x-axis. Angles measured anti-clockwise are positive. So this is positive 60 degrees. And this is positive 120 degrees. Angles measured clockwise are negative. So this is negative 50 degrees. And this is negative 140 degrees. Because the unit circle has a radius of 1 unit, every point on its circumference is 1 unit. These two lines form an angle, and notice that one line lies on the x-axis. If we drew a line perpendicular from up here, it will meet the x-axis here, and this is clearly a right triangle. We can call the opposite side h for height and the adjacent side b for base. The hypotenuse is 1 unit, and so the coordinates of this point are BH, that's XY. See that? Sin theta is equal to opposite over hypotenuse, that is h over 1, which is basically equal to h. Cos theta is equal to adjacent over hypotenuse, which is b over 1, and that's basically b. And so in other words, we could write these sides as sin theta and this one as cos theta, which means the coordinates of this point can be rewritten as cos theta sin theta. That's just replacing b and h. By definition, in a unit circle, the cosine of an angle is the x-coordinate and the sine of an angle is the y-coordinate. From this diagram, tan theta is equal to opposite over adjacent, which is equal to sin theta over cos theta. And this is not just maths drama, it's so real. If you draw the unit circle on a grid, we can confirm this. And so this is the unit circle now on a grid. If you draw an angle of 60 degrees, let us find the trigonometric ratios. So what are the coordinates of P? If your 60 degrees is accurate, point P will have the coordinates 0.5, 0.87. We've said that in a unit circle, the coordinates are cos theta, sin theta. Check with your calculator if cos 60 is not 0.5 and sin 60 0.87. We've also said that tan theta is equal to sin theta over cos theta. 0.87 over 0.5 gives us 1.74. Again, confirm with your calculator if tan 60 is not 1.74. You will find it is. try with another angle, say 30 degrees. This time, the coordinates of P will be 0.87, 0.5. And for sure, cos 30 is 0.87 and sin 30, 0.5. 0.5 over 0.87 gives us 0.57. And if you check, tan 30 is equal to 0.57. Notice that for P to have the coordinates cos theta sin theta, it must lie on the circumference of the unit circle, not anywhere inside or outside the circle. Next, angles greater than 90 degrees. Now, in the first quadrant A of the unit circle, the greatest angle is 90 degrees. If I drew an angle of 120 degrees, point P will now lie in the second quadrant S. Read the coordinates of point P. It's negative 0.5, 0.87. Using the universal coordinates cos theta sin theta, it means that cos 120 degrees is equal to negative 0.5 and sin 120 is equal to 0.87. Tan 120 degrees will therefore be 0.87 over negative 0.5, and that gives us negative 1.74. If you tried 150 degrees, P still lies in the second quadrant. The coordinates of P will be negative 0.87, 0.5, and so cos 150 degrees is equal to negative 0.87 and sin 150 degrees is equal to 0.5. Tan 150 will therefore be 0.5 over negative 0.87, which gives us negative 0.57. How about 210 degrees? If you draw that angle, P is in the third quadrant, T. The coordinates are negative 0.87, negative 0.5. Relating with cos theta sin theta, cos 210 is equal to negative 0.87. Sin 210 will be negative 0.5. And so tan 210 will be equal to negative 0.5 over negative 0.87, giving us negative 0.57. (300 degrees), P will be in the fourth quadrant, C. The coordinates of P are 0.5, negative 0.87. And so cos 300 degrees is equal to 0.5, sin 300 is equal to negative 0.87. Tan 300 will be negative 0.87 over 0.5, that is negative 1.74. In quadrant A, sines, cosines and tangents were positive. A stands for all are positive. In quadrant S, sines are positive, cosines and tangents are negative. S stands for sine is positive. Third quadrant is T. In this quadrant, tangents are positive and the other two are negative. T stands for tangent is positive. In quadrant C, cosines are positive, sines and tangents are negative. C stands for cosine is positive. And so this unit circle should help you remember that green means positive and red means negative. So in the first quadrant, everything is green, meaning it's all positive, and therefore it follows that the tangents are also positive. We get to the second quadrant and it turns green and red. Sines are positive, cosines are negative, and therefore the tangent is negative. In the third quadrant is all red, and it means cosine and sines are negative, which means tangent is positive. In the fourth quadrant, sine is negative and cosine is positive, therefore means tangent is negative. Moving on. Now, when you are required to find the ratios of angles greater than 90 degrees, you will not always have the unit circle. But here is how you get to know them. If you look at the trigonometric ratios we had, you notice there are ratios of 30 and 60 degrees. We are just playing with the negatives and positives. Every angle greater than 90 degrees has what you can call its equivalent acute angle. So the thing you need to know is, first of all, in what quadrant does that angle fall? And then you find the equivalent acute angle and get its trigonometric ratios. And you can now put the negative or positive depending on which quadrant you are dealing with. And so quadrant A has all angles from 0 degrees to 90 degrees. So all angles are acute angles, of course except 90 degrees. And all ratios are positive. By ratios, I mean sines, cosines, and tangents. Quadrant S includes angles greater than 90 degrees up to 180 degrees. So angles in this quadrant are obtuse. Given an obtuse angle theta, to find its acute angle equivalent, we do 180 minus theta. For example, find cos 130 degrees. To find the equivalent acute angle of 130 degrees, we simply do 180 minus 130. That gives us 50 degrees. So you find cos 50 from the tables or your calculator. It's 0.6428. But remember, in this quadrant, cosines are negative. And so cos 130 is equal to negative cos 50 and is equal to negative 0.6428. Quadrant T includes angles greater than 180 up to 270 degrees. And so all angles are reflex angles. In this quadrant, only tangents are positive. Given a reflex angle theta in this quadrant, the equivalent acute angle is given by theta minus 180 degrees. That's the opposite of quadrant S. For example, sine 245 degrees. The equivalent acute angle is equal to 245 minus 180, and that gives us 65 degrees. You find sine 65, and that is 0.9063. But in this quadrant, sines are negative, and so sine 245 degrees is equal to negative sine 65, and that is equal to negative 0.9060. Quadrant C includes all angles greater than 270 degrees up to 360 degrees. All are reflex angles. Given a reflex angle theta in the fourth quadrant, the equivalent acute angle is given by 360 minus theta. For example, cos 350 degrees. The equivalent acute angle of 350 degrees is 360 minus 350, and that is 10 degrees. You find cos 10 degrees, and that is 0.9848. Cosines are positive in this quadrant, and so cos 350 is equal to cos 10 and is equal to 0.9848. Next, negative angles. Negative angles are measured in the clockwise direction. From the unit circle, this is negative 60 degrees. The coordinates of P are 0.5 minus 0.87, and so cos negative 60 degrees is 0.5. Sin negative 60 degrees is minus 0.87. It means tan minus 60 degrees is minus 0.87 over 0.5, and that gives us minus 1.74. This is negative 240 degrees. Point P will now lie in the second quadrant S. Read the coordinates of point P. It's negative 0.5, 0.87. And so cos negative 240 is equal to negative 0.5. Sin negative 240 is equal to 0.87. Tan negative 240 will therefore be 0.87 over negative 0.5, and that gives us negative 1.74. And you can continue all the way up to the first quadrant. Now, when there is no unit circle, you just have to know which quadrant the angle lies. Notice that a rotation of negative 60 degrees or 60 degrees clockwise is the same as a rotation of positive 300 degrees or 300 degrees anti-clockwise. To know the quadrant in which a negative angle lies, we simply add 360 degrees to get the positive equivalent angle. For example, tan negative 205 degrees. To find the quadrant, we need the positive angle. And so we have minus 205 plus 360. That gives us 155 degrees. That angle is in the second quadrant. And so negative 205 degrees is the same as positive 155 degrees. And then you find tan 155 like we did before. Get the acute angle equivalent, which I believe is 25 degrees, and then find the tan of that angle. But remember, tangent in the second quadrant are negative. Next, angles greater than 360 degrees. Now, consider an angle of 420 degrees. This includes a complete tan of 360 degrees and then an additional 60 degrees. That is 420 is equal to 360 plus 60 degrees. 540 degrees is one tan of 360 degrees plus an additional 180 degrees. 800 degrees include two complete rotations and then an addition 80 degrees. To find the ratio of angles greater than 360 degrees, we simply find the ratio of that additional angle. So sine 420 degrees is equal to sine 60, and that is equal to 0.87. That is in the first quadrant. What about cos 510 degrees? 510 degrees is equal to 360 plus 150 degrees. The additional angle is 150 degrees, and so we find cos 150 degrees. This is in the second quadrant. Acute angle equivalent is given by 180 minus 150, and that is 30 degrees. We find cos 30, that is 0.5. In this quadrant, cosine is negative, and so cos 510 is equal to negative cos 30, and that is equal to negative 0.5. Next, finding angles when given the ratio. This is just the opposite of what we've been doing. But to find the angle, you must be given the range. I'll tell you why, but let's first have this example. Find x if cos x is 0.5. for the range of x between 0 and 360 degrees. We first find the acute angle whose cosine is 0.5. The cos inverse of cos x is x. The cos inverse of 0.5 is 60 degrees. The ratio 0.5 was positive, and we know in the unit circle cosine is positive in the first and the fourth quadrants. In the first quadrant, the angle is 60 degrees. What of the fourth quadrant? We find the reflex angle whose acute angle equivalent is 60 degrees. We had seen that to find the acute angle in the fourth quadrant, we do acute angle is equal to 360 minus theta. Now we have the acute angle. We need to find theta. That will be given by theta will be 360 minus the acute angle, giving us 300. And so cos 300 is also 0.5. And so the solution is x is equal to 60 degrees and 300 degrees. Another example, find x if tan x is equal to -1 for the range of x between 0 and 360 degrees. The ratio is negative. We first find the acute angle whose tangent is 1. Tan inverse of tan x is x. Tan inverse of 1 is 45 degrees. However, 45 is in the first quadrant, and in this quadrant, cosine is positive. So 45 degrees is not part of the answer, but it will help us get the answers. Cosine is negative in the second and third quadrants. In the second quadrant, the obtuse angle equivalent of 45 degrees is 180 minus 45, and that gives us 135 degrees. In the third quadrant, the angle will be 180 plus 45, that gives us 225 degrees. And therefore x is equal to 135 degrees and 225 degrees. And now, what with the range? Remember, we've said that sine 420 degrees is equal to sine 60. And so if the range also accommodates 420 degrees, it should be given for the ratio of sine 60 degrees. For example, find x if sine x is negative 0.87 for the range of x between 0 and 1080 degrees. We first find the acute angle whose sine is 0.87. Sine inverse of sine x is x. Sine inverse of 0.87 is 60 degrees. But we had negative 0.87. Sine is negative in the third and fourth quadrant. In the third quadrant, the reflex angle equivalent of 60 degrees is given by 180 plus 60. That gives us 240. So sine 240 is also equal to negative 0.87. Now, 60 degrees will not be part of our solution because that falls in the first quadrant, and yet in that quadrant, signs are positive. So we take 240 degrees. The fourth quadrant, the reflex angle equivalent of 60 degrees is 360 minus 60, and that gives us 300 degrees. So we have the first two values of x, 240 and 300 degrees. But now, suppose we take another round or another rotation and come back to 240 degrees. We would have moved an extra 360 degrees. So we add 360 to 240, and that gives us 600 degrees. We are still within the range. Also, in that second rotation, we will come to 300 degrees. So we also add 360 to 300, and that gives us 660 degrees. Our range is still far. So we go for the third round and we come and find 600 degrees after we have covered 360 degrees. So we add 360 to 600. That gives us 960 degrees. In that same third rotation, we will find 660 degrees. And so we add 360 degrees to that, and that gives us 1020 degrees. If we moved another 360 and add to 960, it will surely surpass our range. And so we stop there. And so those are the values of x within that range. And so the idea is just finding the first two angles and then keep adding 360 degrees. However, you make sure you don't surpass the range. Next, the radian measure. Now, apart from degrees, angles can be given in a unit called radian. 1 radian is the angle subtended at the center of a circle by an arc whose length is equal to the radius of that circle. The angle theta radians is denoted by theta with a superscript c, where c stands for circular measure. The size of an angle in radian is the ratio of the arc length to the radius of the circle. And thus, angle in radians is equal to arc length over radius. And so if an arc AB subtends an angle theta at the center of a circle of radius r, then angle theta is equal to AB over r radians. Recall that the circumference of a circle is given by 2 pi r, and again a whole circle has 360 degrees. Therefore, the angle in radian in a circle is 2 pi r over r, which gives us 2 pi radians. This means that 2 pi radians is equal to 360 degrees. Pi radians is 180 degrees. And therefore, 1 degree will be equal to 180 over pi. Given that pi is 3.142, then 1 radian will be equal to 57.3 degrees. However, in most cases, we prefer to write the angle in form of pi. And that means 360 will be written as 2 pi radians, 180 degrees will be pi radians, 90 degrees is a half pi radians, 45 degrees is a quarter pi radians, and so forth and so forth. And now, trigonometric graphs. Now, the graphs of trigonometric equations, y is equal to sine theta, y is equal to cos theta, and y is equal to tan theta, can be drawn by plotting the values of theta and the corresponding values of y. The angle theta may be in degrees or radians. Just remember pi radians is equal to 180 degrees. We can actually use the unit circle to predict the nature of the graph we should have. Let's start with y is equal to sine theta. First, we need to remember that sine has all to do with the y coordinate of the point on the unit circle. And so we can see how sine changes as theta changes. Using this, we can create the sine curve. When theta is 0 degrees, sine is also 0. In the first quadrant, theta increases and the sine increases as well, up to a maximum of 1 at 90 degrees. In the second quadrant, theta gets larger and larger, but the sine begins to decrease, back to 0 at 180 degrees. third quadrant, theta increases and the sign increases on the negative side up to a maximum of -1 at 270 degrees or 1.5 pi radians. And in the last quadrant, theta increases and the sign decreases back to 0 at 360 degrees or 2 pi radians. In the unit circle, we have completed one revolution and also the wave has formed one cycle. If you were to go beyond 360 degrees, you will have to start another cycle on the unit circle, and the wave will also start from 360 degrees or 2 pi radians. We say that the wave is periodic, that is, it keeps repeating itself. This is the sine graph which has repeated the cycle several times. The highest points are called crests and the lowest points are called troughs. The height of the crest is the amplitude of the graph. In this case, it is 1. Wavelength is the distance between successive crests or troughs. In this case, it's 360 degrees or 2 pi radians. The wave repeats after a distance of 2 pi radians or 360 degrees, and so it has a period of 2 pi radians or 360 degrees. Now for y is equal to cos theta. In the unit circle, cos is the x-coordinate of a point on the unit circle. Watch that the green line tells us how the cosine is changing in the 4 quadrants as theta changes. With that, we can draw the graph. At theta is 0 degrees, cosine is 1. Cos 0 is 1. As theta increases in the first quadrant, cosine reduces up to 0 for 90 degrees. And then increases in the negative as we get into the second quadrant up to a negative maximum at 180 degrees. In the third quadrant, it decreases on the negative side back to 0 at 270 degrees. And then increases back to 1 at 360 degrees or 2 pi radians. And again, this is a complete cycle because we've gone a complete revolution on the unit circle. This pattern will repeat itself if you go past the 2 pi radians or 360 degrees. And so it's also periodic, and this is the graph. It is also an oscillating function with an amplitude of 1 as well. It's similar to the sine curve, it just starts at 1 for 0 degrees. Now let us do y is equal to tan theta. And tan theta is different and actually quite funny. In the unit circle, tan is equal to sine over cosine. Remember that? So when sine is increasing and cosine decreasing, then tangent increases like in the first quadrant. At 90 degrees, sine is 1 and cosine is 0. And so 0 over 1 is infinite. And so tan becomes infinite at that point. In the second quadrant, cosine starts increasing and sine decreasing, and so tangent decreases as well. At 180 degrees, sine is 0 and cosine is 1, and so sine over cosine is 0 over 1, which gives us 0, and so tangent is 0 at that point. In the third quadrant, sine begins increasing and cosine decreases. That means tangent increases. At 270 degrees, sine is 1 and cosine is 0. sine over cosine is equal to 1 over 0, and that gives us infinite, and so tan is infinite at this point again. In the fourth quadrant, sine decreases and cosine increases, and so tangent decreases up to 360 degrees. Here, sine is 0 and cosine is 1. And therefore, it means tangent is 0 over 1, which gives us 0. So on the graph, from 0, it increases infinite at 90 degrees, negative, negative, 0, increases infinite again, negative, negative, back to 0. So this is the weird graphs of the y is equal to tan theta. And so these are the two waves of y is equal to sine theta, that is the red graph, and y is equal to cos theta, the blue graph. The difference is the starting points, and this is because of the complementary nature of sines and cosines. As the angle starts to increase, sine increases, but cosine decreases. At 90, sine is maximum at 1, and cosine is minimum at 0. And it continues. Finally, the sine and cosine rules. So far, we know how to use trigonometric ratios to calculate the sides and angles of a right-angled triangle. Trigonometric ratios can be used to calculate sides and angles of any triangle, but the rules are different. Let's start with the sine rule. Now, consider this triangle ABC. Notice the way the sides and vertices are labeled. Side A is the one that is opposite to vertex A. Side B is the one that is opposite to vertex B, and the same goes for C. AN is a perpendicular to BC, meeting it at N. Using the right angle triangle ANB, sine B is equal to AN over C. Doing cross multiplication, it means AN is equal to C sine B. Call that equation 1. Again, using the right angle triangle ACN, sine C is equal to AN over B. Cross multiplication, it means AN is equal to B sine C. Call that equation 2. Looking at the two equations, the left-hand side are equal. It means we can equate the right-hand sides as well. And so C sine B is equal to B sine C. If we divide both sides by sine B and sine C, we shall get these ones cancel out, and we remain with C over sine C is equal to B over sine B. It follows that A over sine A is equal to B over sine B and is equal to C over sine C. This is the sine rule, and it can be used to calculate the sizes of angles and sides of triangles. Let's take an example. In this triangle, find the unknown sides. C is opposite to angle 60 and 5 is opposite to angle 40. Using the sine rule, C over sine 60 degrees is equal to 5 over sine 40 degrees. C is therefore equal to 5 sine 60 over 40, and That will give us 5 times 0.87 over 0.64, and to one decimal place, that is 6.8 centimeters. We find side A now. Side A is opposite to angle 80 degrees. So we say A over 80 degrees should be equal to 5 over sine 40. And therefore A is equal to 5 over sine 40 times sine 80 degrees. That is 5 over 0.64 times 0.98. That gives us 7.7 centimeters, correct to one decimal place. Further on, now consider this figure. The radius of the circle is R. BC is equal to A. AB is equal to C, and AC is equal to B. Sin theta is equal to a half A over R, because ON bisects BC at right angles. That is equal to A over 2R. Therefore, 2R is equal to A over sin theta. But then theta is equal to angle A. Because the angle subtended by a chord on the circumference of a circle is half that subtended by the same chord at the center of the circle. Therefore, 2R is equal to A over sin A. Similarly, it can be shown that 2R is equal to B over sin B and is equal to C over sin C. And therefore, the sine rule can be extended as A over sin A is equal to B over sin B and is equal to C over sin C and is equal to 2R. Example, in this figure, find the values of A, B, and C if the radius of the circle is 4 centimeters. Using the rule, A over sin A is equal to B over sin B is equal to C over sin C and is equal to 2R. Using the extended sine rule, A over sin A is equal to 2R. So A over sin 60 should be equal to 8. A is equal to 8 times sin 60, and that gives us 6.9 centimeters. B over sin B is equal to 2R. So B over sin 80 degrees should be equal to 8. B is 8 times sin 80, and that is 7.9 centimeters. Finally, C over sin C is equal to 2R. C over sin 40 is equal to 8. C is 8 times sin 40, and that is 5.1 centimeters. The cosine rule. Now consider this triangle ABC. AN is perpendicular to BC at N, and therefore triangle ABN and ACN are right-angled triangles. Using Pythagoras' theorem, in triangle ANC, B squared is equal to H squared plus A minus X squared. Expanding that bracket, we shall have B squared is equal to H squared plus A squared minus 2AX plus X squared. We call that equation 1. In triangle A and B, C squared is equal to H squared plus X squared. And therefore, H squared is equal to C squared minus X squared according to Pythagoras' theorem. We call that equation 2. Substituting H squared in equation 2, we get B squared is equal to C squared minus squared plus A squared minus 2AX plus X squared. And that gives us C squared plus a squared minus 2ax. Cos b is equal to x over c. Therefore, x is equal to c cos b. That means b squared is equal to c squared plus a squared minus 2ac cos b. In the same way, it can be shown that c squared is equal to a squared plus b squared minus 2ab cos c, and a squared is equal to b squared plus c squared minus 2bc cos a. Let's take an example. Find the length of AB in this triangle. Using the cosine rule, we express the unknown side in terms of the other sides. And so c squared is equal to a squared plus b squared minus 2ab cos c. That is equal to 5 squared plus 6 squared minus 2 times 5 times 6 times cos 120. Cos 120 is equal to negative 0.5. Therefore, c squared is equal to 25 plus 36 minus 60 times negative 0.5. That gives us 61 plus 30. And given to 2 decimal places, that is 9.54 centimeters.
But in almost any class that you go into, you need to make sure that you're at the starting point. People come in with different backgrounds, different preparations, and so you're not all on the first day at exactly the same place. And so you can go on and learn math. You may need tutorials, you may need tutors, etc., to get your foundation solid so that you can build the next course on it. But math is not so complicated that most people can't learn high school math and certainly the introductory courses in university. If you want to go on and major in math or do honors in math or do a career in math, you really do need to be good at it. But I think too many people stop out too soon because they've had bad experiences. I think math teachers have a lot of responsibility for that. We haven't taught it so well. We haven't provided the resources that people need. And so I think if you need help, you need to get it, and you need to get it early. And you need to work at it.